What if we told you that you exist in another universe that you were not aware of? While that may sound scary, it is not impossible to find a copy of you or your loved one living in an entirely different universe. This is because of the theory of multiple or parallel universes. However, while some scientists dismiss the theory as fiction, more proof is coming in about the existence of these alternate universes. What are parallel universes, and how do they affect you? All these and much more as we dive into how scientists have finally found proof for the existence of parallel universes. Has it ever crossed your mind if there are other forms of life out there in the universe? Humans have been preoccupied with that question since time immemorial, but of course, questions like this are why we are humans. Meanwhile, scientists do much more than asking about other forms of life though, because some of them have theorized that there may be another universe out there right alongside ours. Some believe there could be an infinite number of such universes, which they call parallel universes. This concept looks straight out of science fiction novels and movies, and there have certainly been enough of those over the years to arouse the curiosity of readers and viewers everywhere. The idea of parallel universes dates back to 1954, when Hugh Everett III, a Princeton University student, developed the radical notion that parallel universes, or universes that look precisely like and related to our universe, exist. These parallel universes branch off from ours, and our universe branches off from others. There are many practical dimensions to this bold theory because it implies that in parallel universes, the world wars might have different outcomes, for example. Also, species such as dinosaurs might have lived in particular parallel universes or are still living there. In fact, humans themselves might have become extinct in certain parallel universes. Many people doubted this budding scientist and his radical idea. However, Everett's many worlds theory, as it came to be known, was his attempt to answer some unanswered questions raised by the results of experiments performed in the growing field of quantum physics. Quantum physics studies stuff at the quantum level, the smallest level scientists have detected so far. Quantum matter, which exists on the subatomic level, appears to behave erratically at times, as opposed to the orderliness observed in many other spheres. This led scientists to believe there are other scientific laws at work, even though we don't know about them yet. For example, scientists studying quantum matter soon realized that quantum particles such as photons seem to take different forms arbitrarily. Scientists who observed photons noticed that sometimes they acted like particles and they behaved like waves at other times. That's like you being a solid human being one minute and gas the next. This phenomenon is called the Heisenberg uncertainty principle. Physicist Werner Heisenberg proposed that we affect the behavior of quantum matter simply by observing it. Weird, right? Another physicist, Niels Bohr, agreed and took it to another level by theorizing that quantum particles exist in all possible states at once, and when we observe them, our observation affects their behavior, forcing them to choose one state at that moment in time. Well, you can view Everett's many worlds theory as an alternative to Bohr's view of quantum matter. Everett posited that observing quantum matter causes an actual split in the universe rather than a switching between states. So the universe literally duplicates and splits into multiple parallel universes for each possible state of quantum matter. Meanwhile, the many worlds theory has some implications that make some scientists uncomfortable. For example, suppose you've ever encountered a situation which one possible outcome was death. Then by Everett's theory, there must be a parallel universe out there in which you died. Everett's approach was also controversial because it conflicts with our fundamental understanding of the concept of time. Due to these, Everett's theory was considered far-fetched for many years. Still recently, scientists have become interested in it again after some scientists conducted thought experiments that seem to prove the Everett's theory is theoretically possible. Interestingly, Everett's theory is not the only alternative theory that attempts to explain quantum mechanics. Another theory known as string theory claims that there exist particles even smaller than quantum matter. String theory also claims that parallel universes can exist. However, working our way from the Big Bang, we will pretty much arrive at parallel universes. How? Well, bear in mind that we have a boundary to the part of the universe that we can access, a boundary in time. The universe as we see it began some 13.8 billion years ago in the Big Bang, where the universe was hot, dense, filled with matter and radiation, and was expanding, cooling, and gravitating from that initial state. The farther we look back in space, the farther we wind up looking back in time, all the way to the boundary of the hot Big Bang. However, you can't go back to arbitrarily early times because if the universe had exceeded a certain temperature and density, it would have properties we specifically observe it not to have. Instead, observations are far more consistent with the notion that the hot Big Bang was preceded and set up by a period of cosmic inflation, which stretched the universe's curvature so that it would be indistinguishable from flat. It then inflated away any problematic, unobserved high-energy relics predicted to form at high temperatures. This gave the universe the same energy density everywhere, with quantum fluctuations which occur during inflation superimposed atop the uniform energy background. As inflation goes on, there's a certain probability that the field will roll into the valley where inflation ends, a certain probability that it won't and inflation will continue, and even a certain probability that the field will roll in the wrong direction, taking us farther away from inflation's end. And because the inflating universe continuously creates new space, all of these possibilities can coincide in different regions of the inflating universe. As inflation continues, stretching the universe and creating new space, in some places the field rolls into the valley, bringing inflation to an end. This results in the creation of hot Big Bangs in those regions, what we might call the universe. In between those universes is more inflating space, where inflation doesn't end but continues, so new space gets created as the universe expands. In other places, the field rolls into the valley, bringing inflation to an end with more hot Big Bangs and even more universes. Meanwhile, inflation continues in the regions where it didn't end, creating more space. Now we have a scenario where we get enough inflation to set up the hot Big Bang with the properties we observe and always get a multiverse, one where independent, separate universes are constantly being born, forever separated from one another by space that continues to inflate eternally, while new universes and new hot Big Bangs continue to spawn. You cannot transfer anything between these universes. Even though every universe emerged from the same small region of space, no information can be transferred between them. They are not causally connected. There are many skeptics of the theory of parallel universes, including scientists. One of their biggest criticism is that you can't really test it. However, an experiment seems to have changed all of that. The experiment was a cosmic ray detection test that found particles that just could be from outside our universe. Talk about august visitors. NASA's Antarctic Impulsive Transient Antenna, ANITA, uses a giant balloon to haul delicate electronic antennas high into the cold, dry air above Antarctica, where there is little or no radio noise to distort its findings. There is a constant wind of high-energy particles coming from outer space, some of which are 1,000,000 times more powerful than anything we can generate ourselves. Low-energy particles, known as neutrinos, can pass completely through the Earth, barely interacting with the substance of our planet at all. But higher-energy objects come to a halt thanks to the solid matter of the Earth. This means that high-energy particles can only be detected coming down from outer space. But to detect a heavier particle, known as a tau neutrino, coming up out of the Earth, would imply that these particles are actually traveling backward in time. This suggests the evidence of a parallel universe. However, many scientists have explained away the phenomenon observed by ANITA, claiming that while the finding is interesting, it was due to some other things apart from parallel universes. However, that is not surprising. Past astronomers believed our planet to be alone, then our solar system to be alone, so the existence of multiple universes isn't a theory to dump. But then, how can we test for the existence of parallel universes? Well, if our universe collided with another, it would offer some evidence. Some theorists have suggested that colliding universes could leave cold spots or hot spots on the cosmic microwave background, CMB, the afterglow of the Big Bang. If so, we should be able to detect those spots with advanced sky surveys. Gravitational waves, which are ripples in the fabric of space-time, might also provide evidence to support the theory of cosmic inflation. The theory predicts that gravitational waves left over from the Big Bang could put tiny curls into the CMB, which some telescopes are actively searching for today. If researchers can spot such curls in the CMB as they thought they did back in 2014, it could ultimately boost support for the idea that there's another you out there going about their daily life in an alternate universe, proving sci-fi writers correct once again. However, before that happens, there is a connection between parallel universes and two other mysterious and scary space phenomena: black holes and white holes. Black holes are those terrifying objects in deep space that swallow everything that comes near them. They are formed when giant stars collapse on themselves, creating very dense masses that have gravitational forces so strong that nothing can escape from their attraction, not even light. White holes are the opposite of black holes because they push out everything inside them and nothing can go inside. There are various theories about the formation of white holes, which we won't go into in this video, but how are the three connected? In essence, every white hole could generate other big bangs, generating multiple universes inside our own or outside its radius or boundaries. Hence, the laws of physics there would be different. Reality could be made from antimatter, or possibly time wouldn't be positive and unidirectional. Probably these universes would be mirrors to our universe, with divergent timelines based on different quantum states coming to life, confirming quantum superposition. Let's hear what you think of parallel universes in the comments section below.